Hello, this is section 3.6 for Calc AB, and today we're talking about optimization problems. And we've done another type of word problems called related rates, and one of the biggest differences between these two types of word problems is with related rates, the biggest thing was you needed to make sure that you answered with generally in a complete sentence with units. Whereas optimization problems, and you can see it says right here, problem-solving strategy for applied maximum and minimum problems, meaning you're finding the you're finding the optimal, whatever you're referring to, the minimum or maximum amount. And we have to justify our maximums, just like we've been doing in all the sections leading up to this. So that's the big thing with optimization problems is you have to justify your answer. So that's going to be really big. Whereas related rates, we didn't have to necessarily justify. So let's do a problem and then we'll go through and read this box to make sense of it. So I'm going to scroll down. Let's do this first one. So the sum of one number x and 2 times the second number is 90. That's an equation. So I wrote that over here. X plus 2y equals 90. All right. And then it says find x and y if the product of x and the square of y, so I wrote that here, product of x times y squared, is to be a maximum. Okay, so I want to maximize this product. Now, you already know, if you want to find the maximum, you first find the derivative, set it equal to 0 to get your critical numbers. You test the endpoints and any critical numbers that fall within the range that we care about. And you're going to use the same concept here. But the problem is, how are you going to do the derivative if you've got two different variables? And we don't want to have to deal with two different variables. And that's what this other equation helps us with. We can easily solve for x, subtract over the 2y, substitute this binomial in, and now you have a new function that's in terms of y. Now you can do the derivative much easier. And that's what we do. So I went ahead and distributed the y squared so we could have a nice pretty derivative. So then I did the derivative, and notice I label it when I do the derivative. And then set that derivative equal to 0 to get your critical numbers, and we get critical numbers at 0 and 30. Those are our two critical numbers. So I went over here to the side, and I made my first derivative number line test to see what's happening at 0 and 30. And we want to plug in those intervals back into your derivative, and we see that at 0 we have a minimum, and at 30 we have a maximum, and it's asking for that maximum. So I put over here, because the derivative at 30 changes from positive to negative, then the maximum will be when x equals 30 and y equals 30. Now, you might already see a problem and you might say, Cogswell, wait. You said when it's a maximum, we have to do a candidates test, and that is true. And if you plugged in 0 for y, you'd get x is 90, 0 for x, you get y is 90. And you could create a candidates test and check 0, 30, and 90 and figure out what is the maximum. I would accept either answer. Rarely ever have we seen this pop up on a free response part of an AP. I don't even know if it ever has been on a free response part of an AP exam. And generally with these types of problems, it's not going to be the endpoints. Like you already know, you're not going to make 0 be an x or a y to get the biggest possible product. So that's why a lot of times you can logically rule out the endpoints. But if you did a candidates test, I would accept that as well. Okay. Now let's go back and see if we can make sense of this box. So assign symbols to all given quantities to be determined. Well, that's our x and y. When feasible, make a sketch. Write a primary equation for the quantity that is to be maximized. That was this equation here. We're trying to maximize that product. And you can label it however you want. And you can just call it F if you want. You don't have to write this x comma y. This may involve the use of a secondary equation relating the independent variables of the primary equation. Okay, so here's where I skipped a sentence. Reduce the primary equation to have one single independent variable. So that's where we needed this secondary equation to substitute in. All right, and then 4 says determine the domain of the primary equation, that is, determine the values for which the stated problem makes sense. And that's referring to consider your endpoints. What are the extremes that we even care about? And go from there. Then determine the desired maximum value of the calculus techniques discussed in sections 3.1 and 3.4, meaning your first derivative test, get your critical numbers. When working on a closed interval, compare values of f of x at critical numbers and the endpoints, and you have to justify. And then finally, find values of all variables and make sure you answer the original question. Okay, so, all right, I'm going to scroll down. Let's try another one. So a farmer wishes to use a fence, rectangular area next to a barn. If he has 2,000 feet of wire, what is the maximum area he can enclose? Okay, so maximum area he can enclose. That's what I'm trying to maximize, is the area of that rectangular fence right there. But again, we have 2 different variables we need to substitute. And they said we have 2,000 feet of wire. So I made x and x, and we have 1 y. So 2,000 equals to 2x plus y. Solve for whatever the easy variable is, solved for y. And that's what we'll substitute into our area formula. And now we can do the derivative very easily. So that's what I did. Did the derivative, set it equal to 0, got x equals 500. Okay. Now, remember we talked about first derivative test and second derivative test. These problems, when you're working with polynomial functions, the second derivative test is so nice because, guys, if you do the second derivative, you get -4. That means that my area function is always concave down. So at my critical number of 500, it must be a maximum. Oh, and that helps me justify. So because the first derivative at 500 equals 0 and the double derivative at 500 was less than 0, so we do have a critical number and it's the double derivative is less than 0, then the maximum area is, and then here's where it said, be careful, make sure you answer the question. It wanted, what is the maximum area? If you tell me the answer is 500, that's not the maximum area. You need to plug 500 back into your area formula here to give me the maximum area, which is this 500,000 feet squared. And make sure you include units. But isn't that cool that we actually got to use the second derivative test to justify? So when it's a polynomial, I could have done that up here as well. When it's a polynomial, you can use that double derivative or that second derivative test. Okay, here's another one. A page contains 200 square inches and must have 2-inch margins at the top and bottom, 1-inch margins on each side. What dimensions will allow the most print on the rectangular page? So the print is the inside, XY. So I made that what we're going to be optimizing. Okay. But again, just like normal, we have it's in terms of X and Y. So what else did they give us so we can get rid of that? A page contains 200 square inches. So that's the overall page. So notice I did X plus 2, Y plus 4 to add in the margins. And I multiplied and set that equal to 200 so I could solve for one of these variables. So I had to divide over the binomial and subtract over 2. But this lovely expression can replace the X. But that's what you're going to find the derivative of. Now I cleaned it up a little bit so I could do low D high minus high D low over low low. Clean that up, set it equal to 0, got my potential critical numbers. I got a -24 that we obviously throw out, and we did get 16. Yay! So we tested out 16 in the first derivative to confirm that we do go from increasing to decreasing. It's a max, a relative max. So because the derivative changes from positive to negative at 16, you're good to go. Okay, and make sure you give me the dimensions. And in this one, you got X and Y. It says, what dimensions will allow the most print on the rectangular page? So you want to give me the dimensions of the overall page. So we got our X and Y to be 16. Well, we got 16, and that's here. That was your Y value. So if you plug 16 in there, add 4 to that, that's where that 20 is coming from. And then to get the other one, you can plug 16 over here to get your x value. And whatever x value, it must have been 6, or it must have been 8, excuse me, and then add 2 to that and you get 10. So, and notice there's the units. So make sure you answer what it wants. You have to be a little bit careful there. All right, this one's pretty straightforward. A volume problem, you can go through that on your own. These show up a lot. What a rectangle is bounded by the x-axis in a semicircle. What length and width should the rectangle have so that its area is a maximum? All right, so I graphed it so you can see the visual, and I want to know what is the biggest rectangle that can fit in that semicircle. So again, you're maximizing the rectangle's area, so that's what we're starting with. And then really technically this should be x would be your base and y is going to be your height. So I'm going to use this formula, but you have to be careful because the base, notice that just the right side would be x, so you'll want to double that. So that's where we're getting 2x from. And then the height will get replaced with y, but y equals this function in terms of x already. So that worked out really nice. Okay, but now you got to do this derivative. So do that derivative, set it equal to 0. It looks like I pulled out my calculator to help us out a little bit. We got our critical number. And then I made sure that I tested using the derivative to make sure it is in fact a maximum. And I think we're good to go. So because the derivative at 3.5355 changes from positive to negative, then the length is, and so forth. Okay. So please make sure that you do your homework. You have to practice these types of problems. Once you get used to setting up what you're optimizing, using other information to make it in terms of one variable, find the derivative, set it equal to 0. It's a pretty straightforward process. It's not too bad. And you can use first or second derivative tests to justify your answer, or the candidates test as well, if you can identify the endpoints really easily. So, but again, very rarely have we seen this pop up on the free response part of the AP exam. But these are really good problems and they can be a little bit fun, but you have to do your homework. You have to practice them. Okay? All right, email me if you have any questions.